go. Share and share screen. Right. Here we go. You know, learning organic chemistry, especially at the beginning, is a lot like learning a language. There's a lot of things to know in the first couple of chapters. So I'm not trying to come off sounding like a meanie or trying to scare you. I definitely wouldn't do that to a student. I'm not here to intimidate. I'm here to educate. But I just want to, put the bug in your ear that the first chapter, chapter 10 in this class is a long chapter, and there's a lot of things to learn in this chapter. But it's one of those things where if you put a lot of effort in at the beginning and learning, trying to put your best effort forward in learning the language of organic chemistry, the other chapters, generally speaking, come a little bit more naturally. So with that in mind, let's take a look at organic chemistry. Now, again, I know you've all passed Introduction to Chemistry 1, whether you took it at Pikes Peak Community College or another college or university. And in Introduction to Chemistry 1, you spend a lot of time talking about the periodic table. You talk about all the alkali metals and the alkaline earths and the transition metals and the halogens and the noble gases and all these things. So you spend a lot of time talking about a lot of different elements. But then when you get to organic chemistry, you basically spend an entire semester focused on one element in the entire periodic table. And if you're wondering, why do I have to spend an entire semester studying one element? Well, there's some really good reasons for that. I'd say, first of all, if you're interested in the healthcare industry, virtually all pharmaceuticals or all drugs contain carbon atoms and are organic compounds. Our bodies, if you're interested in biological chemistry or biochemistry, our bodies are largely made up of carbon-based molecules. Okay, and there's many other reasons, and I've summarized some more of those right here. In the first one, just in terms of bonding, is that carbon forms stable covalent bonds with other carbon atoms. And you think, well, that doesn't sound that interesting. Well, in fact, it's quite unique. If you think about something like a sodium atom that you would have discussed in general chemistry, you never saw a sodium covalently bound to another sodium. That's impossible. Okay, that cannot happen. But carbon atoms can bind to each other. And in fact, carbon can form up to four covalent bonds, with other carbon atoms. So one of the most important things you have to remember is that carbon always forms four covalent bonds. You're going to see carbon always forms four bonds. No exceptions to that. Okay. And what's interesting is that carbon can form four covalent bonds with other carbon atoms and with other atoms as well, okay? Because carbon atoms form stable bonds with other elements like oxygen, nitrogen, sulfur, the halogens. The halogens are chlorine, fluorine, bromine, and iodine. You would have learned that in Introduction to Chemistry 1. Carbon can also form bonds with phosphorus and silicon and other elements. So it says here in the last bullet point that the presence of these other elements confers many new physical and chemical properties on an organic compound. So organic compounds, compounds that contain carbon, since carbon can bond to so many other elements, organic compounds have wide ranges of chemical properties and physical properties. So organic chemistry, in a nutshell, is just a very interesting subject. Now, obviously I'm biased, but it's just true. Reason number 3, it says that carbon atoms, not only can they form single bonds, they can form double or triple bonds with other atoms to produce a variety of structures with differing properties. If you take a look at this molecule down here, this is called ethene, or the common name of it is ethylene. You don't have to have that memorized right now. The important point is that the carbons have a double bond, right? So there's a double bond there. They also have single bonds, but they have a double bond. Not only can a carbon form a double bond with another carbon, you can see here that it's formed a double bond with an oxygen, like this. In this molecule here, this is formaldehyde. Formaldehyde, and if you've been in a biology lab, you're probably aware of what formaldehyde is used for. Even carbon dioxide, right? If you draw CO2, if you draw the Lewis structure of carbon dioxide, you can see that that carbon atom has a total of 4 bonds and that it has 2 double bonds. So that's an example of carbon having 2 double bonds. Also, carbon can form triple bonds. So triple bonds, that's kind of interesting. So if you take a look at this carbon and this molecule here, it has a triple bond to this carbon. This molecule is acetylene. If you've ever done any welding before, sometimes acetylene is used as a gas in welding. And then this molecule here, excuse me, you can see that carbon can form a triple bond to a nitrogen atom as well. Kind of interesting stuff. All right, so double bonds, triple bonds, single bonds, bonds to other elements, and carbon can form bonds to itself. More reasons. Reason number 4, it says the number of ways to arrange carbon and other atoms is nearly limitless. Okay, not only can we form chains of carbon, but we can have branched chains. And if you're like, what does he mean by a branched chain? We'll take a look at examples of that. And carbon can form ring structures like is shown here, and it can also form linear chains like are shown here. So that opens up, Pandora's box to all kinds of other possibilities if we can form rings and chains and branched chains. Now it says here that 2 organic compounds can even have the same number and kinds of atoms, but completely different structures and thus different properties, and we call those isomers. And we're going to get into more detail on isomers later on. Now let's talk about some differences between organic and inorganic compounds. So if you go back to your general chemistry days or your introduction to chemistry days, inorganic compounds, what's an example of an inorganic compound? Well, an ionic compound would be an inorganic compound, something like sodium chloride or magnesium chloride, right? Those are inorganic compounds, right? Because they're made from metals and nonmetals. Excuse me. Organic compounds all contain carbon, and generally speaking, they virtually all contain only nonmetals. So if I make the simplest possible organic compound, which is called methane, which has a molecular formula of CH4, it contains only carbon and hydrogen. And carbon and hydrogen are both nonmetals. So what else? In terms of bonding, organic compounds have covalent bonds. And you should know that a covalent bond results from the sharing of electrons. So if we think about this molecule right here, methane, if I draw the Lewis structure, it has 4 bonds on the carbon, right? Carbon always has 4 bonds. So 1 bond to each of the hydrogens. And you know that each one of these bonds is the sharing of 2 electrons. That's another cardinal rule of chemistry, is that there are always 2 electrons in a bond. Now, inorganic compounds, on the other hand, they usually have ionic bonds. So if I go back to my NaCl, right, you probably remember this, that sodium, if you look at the periodic table, sodium is in group 1A and has 1 valence electron, and it will lose that electron to become a sodium cation, and it will transfer that electron to the chlorine to make chloride. And this is an ionic compound. So ionic bonds are a result of electrostatic attraction, okay, because we have an attraction between positive and negative in the ionic compound. So those are some important differences between organic and inorganic compounds in terms of bonding. Now, in terms of the structure of an organic versus an inorganic molecule, this is kind of a very quick summary, but for organic compounds are molecules. Okay, if you think about something like table sugar, the proper name of table sugar is sucrose, and sucrose is only made from carbon, hydrogen, and oxygen. If you've ever studied biology before, I'm sure you've heard of glucose. So glucose, and if you haven't, don't worry about it. Glucose, the molecular formula of glucose is C6H12O6. Glucose is made completely of nonmetals, carbon, hydrogen, and oxygen. None of those are metals. And therefore, glucose is just a molecule. It's all held together by covalent bonds. And it is also a non-electrolyte. So organic molecules, generally speaking, are non-electrolytes. And if you're like, what's a non-electrolyte? That is also something that you should be aware of from Introduction to Chemistry 1. And a non-electrolyte is some kind of compound or molecule that when you put it in water, it does not ionize or it does not dissociate into ions. So for example, if I take glucose, solid glucose, and if I put it in water, I end up with glucose, but instead of solid, it's going to be aqueous. That means it's in solution. Now, conversely, in inorganic compounds, they do not exist as molecules. So you never talk about a sodium chloride molecule. In fact, it feels just creepy for me to say that. There's no such thing, okay? Sodium chloride exists as a three-dimensional crystal, right? You would remember, hopefully, that if you pick up a piece of, table salt and you look at it, it's got this cubic shape to it, right? And we have the ions alternating, right? We have a sodium and a chlorine and a sodium and a chlorine, okay? Like this in our cubic structure, like that. Okay, so inorganic compounds are three-dimensional crystal structures, and they're often water soluble and they dissociate into ions. That means that they are electrolytes. So that means that if I take sodium chloride, right, just good old table salt, solid table salt that I could hold in my hand, and I see those white crystals, if I put them in water, I'm going to end up with the sodium ion, right? And that's going to be in water plus a chloride anion, which will also be aqueous because it is solvated by the water. So that's the big difference between a non-electrolyte and an electrolyte. So again, organic compounds are molecules and they are non-electrolytes. And you might be wondering, are there any exceptions to this rule? And the answer is, yeah, there are some. Okay, there are some exceptions to that rule, but that's not really important for chapter 10 or for chapter 11. So don't stress about exceptions for the first exam, okay? Remember, my job is not to try to trick you, okay? My job is to try to teach you organic chemistry to the best of my ability and then to test you on the subject, not to try to make your life miserable, okay? So Mr. Dion's not going to just focus on a bunch of little exceptions, okay? On a bunch of minutia. Now, in terms of organic and inorganic compound differences in melting points and boiling points, generally speaking, organic compounds have lower melting points and boiling points, and inorganic compounds have high melting points and boiling points. Look, I'll make this quick, okay? If you've ever done any cooking at home, I told you that sucrose, table sugar, is an organic compound. If you took some table sugar and put it in a frying pan and turn up the heat, can you melt sugar? Well, maybe somebody in the class has never cooked before, but I'll tell you right now, you can melt sugar very easily. In fact, it's one of the ways that you make a caramel sauce. So melting an organic compound is very easy. Organic compounds have low melting points because the forces that hold the sucrose molecules together are actually quite weak. So the intermolecular forces are broken fairly easily. On the other side of things, for inorganic compounds, if you were to take some table salt and put that in a frying pan and turn it up to the same heat as you had that sucrose that melted, it's not going to melt. Okay, it's going to remain a solid. And the reason why is that inorganics have high melting points because ionic bonds, that positive and negative, that those opposites attracting, are much stronger bonds or intermolecular forces, and therefore they require more energy to break those, to go from the solid phase to the liquid phase, let's say. Let's move on and talk about water solubility down here. So water solubility, organic compounds, generally speaking, again, there are exceptions to this, but generally speaking, organic compounds are nonpolar. Why would this be? Because the organic compounds that we're going to look at most of the time tonight are going to be what we call hydrocarbons, which are organic compounds that are only made from carbon and hydrogen. So the good news is, first two chapters mostly focused on two elements. You're like, well, that's I can handle that. Okay. Well, I can tell you right now that a carbon-carbon bond or a carbon-hydrogen bond, both of these are nonpolar bonds. Okay. So you probably remember that water, H2O is polar. Okay. And you probably also remember the rule, like dissolves like. So nonpolar and polar are not like. So that is why oil and water don't mix, right? If you try to mix, cooking oil with water, they don't mix in each other very well at all. Whereas an inorganic compound like sodium chloride, it's an electrolyte, right? It's water soluble, and it's easily or readily going to dissociate into its ions. Another example of this with organic compounds that I like to tell my students is, you know, if you've ever heard of octane, if you've ever filled up your car before, you've probably heard of octane or seen a gasoline's octane rating. Well, octane is an organic molecule. It's made only from carbon-carbon and carbon-hydrogen bonds. So that means it's a nonpolar molecule. And if you've ever spilled gasoline on a puddle, maybe at a gas station on a rainy day, you'll notice that the gas kind of makes like a pool on top, and it makes these funky colors. And the reason why it floats on top is because it's nonpolar. Another example would be an oil spill, right? Sometimes you'll see in the news these very tragic events where maybe an oil tanker or something will have a hole in it and then it'll leak all kinds of oil. The oil does not float or does not sink to the bottom of the ocean. Rather, it remains on the surface of the ocean, where it can create, wreak a lot of havoc on aquatic life and also on birds that, like to float on top of the water. So organic compounds, again, water insoluble as a result of nonpolar bonds. This table, I could go into a lot of detail on this, and I did in my video, so maybe you can take a look at that. But this table just basically summarizes the differences between organic compounds and inorganic compounds. And the compounds they've chosen to compare in this particular table are butane, which is an organic compound. The molecular formula is C4H10. In fact, I could draw the Lewis structure of butane out for you just to show you what it looks like. If we have 4 carbon atoms bound together like this, carbon always has 4 bonds, so I have to have 1, 2, 3 hydrogens attached to this carbon. I must have 2 here, I must have 2 here, and I must have 3 on this one here. So this is a butane molecule. So this would be a completely non-polar molecule. If I look at my sodium chloride, NaCl is an ionic compound, right? It's comprised of the sodium cation and the chloride anion. And if you're like, well, why did they choose these two compounds to compare? The reason why is because they both have very similar molar masses, okay? Both of their molar masses are around 58 grams per mole. But then if you look at these, okay, well, the organic compound has covalent bonding. The ionic compound, or the inorganic compound, excuse me, has ionic bonding. Look at this. At room temperature and atmospheric pressure, butane is a gas, right? If you've ever used a Bic lighter before, the gas, the liquid you can see in there is butane. Now, the reason it's a liquid in there is because it's under pressure. But if you release the pressure valve in a Bic lighter, the liquid inside, the butane, becomes a gas readily. Whereas sodium chloride is a solid room temperature. This is a result of the intermolecular forces. The boiling points and melting points and solubilities, we looked at those already. And the flammability, we actually do an experiment in lab number 1 where we test the flammability of an inorganic compound versus the flammability of an organic compound. And you can probably already guess what's going to happen based off of the information of this table. There you go, kind of a giveaway for one of the parts of the experiment in lab number 1. So let's get into what are called hydrocarbons. I will take a break in a little bit, but I want to talk a little bit more about organic chemistry and about molecules called hydrocarbons. And the good news is we start with molecules that only have 2 elements, literally just 2, carbon and hydrogen. That's it. And hydrocarbons must be nonpolar molecules because, again, they only contain carbon-carbon bonds and carbon-hydrogen bonds. And I told you that these are nonpolar bonds. I don't want to sound like a broken record, and I don't expect you to remember everything you've ever learned in your life, but you should know why these are nonpolar bonds. And the reason why is because the difference in electronegativity between carbon and carbon is 0, therefore there's no dipole. And the difference in electronegativity between carbon and hydrogen is so small that there is no dipole. So hydrocarbons, of course, are not going to be soluble in water because they're nonpolar and water is polar, right? Like dissolves like. Um, but they are soluble. What are they soluble in? They're soluble in typical nonpolar organic solvents, right? These are both nonpolar, right? Like dissolves like. And if you're wondering what the heck is toluene and pentane, well, we'll look at those in more detail later on. But what you need to understand from this slide, I'd say the take-home message of this bullet point is just understanding this rule. That if I have a nonpolar organic compound, right, if I have a nonpolar hydrocarbon, it's going to solubilize in a nonpolar solvent, okay? And it's going to be insoluble in water. Now let's talk about what we call the substituted hydrocarbons. It says here that hydrocarbons are constructed of chains or rings of carbon atoms with sufficient hydrogens to fulfill carbon's need for 4 bonds. So a substituted hydrocarbon is one in which one or more of the hydrogen atoms is replaced by another atom or a group of atoms. So when it says here hydrocarbons are constructed of chains or rings of carbon atoms, this bullet point, what it means is that you could have a chain of carbons like this. Like let's say you had 5 carbons in a row. Obviously, none of them have 4 bonds yet, but this is an incomplete structure. What it's saying down here is that, you know, you could, if these are all hydrogens, let's say, now let me take the time to fill them all in. And if you're wondering, is there an easier way to do this? The answer is yes, and we'll try to go over that tonight. Okay, what it's saying here in this bullet point is that you could replace one of those hydrogens with another carbon. So if I have 1, 2, 3, 4, there we go. So I could put another carbon down here. That's all it's really saying. And then of course you'd want to fill all of these up to make sure they all have 4 bonds. So you'd put in all your hydrogens, so on and so forth. You can see that this gets exhausting writing all of these hydrogens. But it's one of those things you have to go over at the beginning of organic chemistry, right? We're learning the language. Learning a language is time consuming. Okay. 1 second here. All right. Okay, so this slide just kind of gives you a division of the family of hydrocarbons. So unfortunately, it's not just as simple as hydrocarbons. You know, there's sort of some subfamilies, I guess. So we can first start out by dividing hydrocarbons into 2 major classes, namely what we call the aromatic hydrocarbons and the aliphatic hydrocarbons. I'm going to mostly focus on the aliphatic hydrocarbons tonight. In fact, I'm mostly going to focus on alkanes and cycloalkanes. Alkanes and cycloalkanes, they, of course, are hydrocarbons, so they're only comprised of carbon and hydrogen. But the good news is that they only have single bonds. But in an alkane, we have single bonds and we have no rings. Whereas in a cycloalkane, we only have single bonds and the carbon atoms are bound in a ring. Now here you have 4 carbon atoms in a ring, right? 1, 2, 3, 4, like this, okay? So we're going to go over alkanes and cycloalkanes in gross and dirty detail. In chapter 11, so something to look forward to, right? Everybody needs something to look forward to. So in chapter 11, we will discuss alkenes and alkynes. So that's something that we'll take a look at next week. Okay, so let's talk about alkanes. So alkanes are compounds that contain only carbon-carbon and carbon-hydrogen single bonds. Okay, only single bonds. We call these saturated hydrocarbons because they have no double or triple bonds. Another way to describe this bullet point here would be to say you have the maximum number of hydrogens for every carbon atom in your molecule. The molecule can't hold any more hydrogens. If you tried to add another one, can't do it, okay? Whereas alkenes and alkynes, and let me just back up one slide here for a quick second. You notice that alkenes and alkynes have double and triple bonds in them, okay? So alkenes and alkynes are unsaturated because they don't contain the maximum number of hydrogens per carbon atom. Another way of saying that is saying they have at least one carbon-carbon double or one carbon-carbon triple bond. Okay, so every time you see a double bond or a triple bond, we call that an unsaturated hydrocarbon. All right, so you've probably all heard of saturated fats and unsaturated fats. They're directly related to this concept. So an unsaturated fat is simply a fat that does not have the maximum number of hydrogens per carbon atom in the molecule, and a saturated fat does have the maximum number of hydrogens per carbon atom in the molecule. It says here the cyclic structure of hydrocarbons. So I wanted to just kind of wait to tell you a little bit more about aromatic hydrocarbons. So it says here some hydrocarbons are cyclic. That just means they form a ring. Okay, they form some kind of ring. Okay, a closed ring. Aromatic hydrocarbons contain a benzene ring or a related structure. Look, you're going to see this molecule enough that I'll just tell you right now, you're going to have to kind of memorize the structure of benzene. In fact, in your Chemistry 101, if you took this class at PPCC, you may have seen the benzene molecule before. And we call that an aromatic hydrocarbon. And if you're like, what's the difference between cyclohexane and benzene? Well, there's a big difference. You can see that the benzene molecule, let me just clear everything off of here. The benzene molecule has a molecular formula of C6H6. And you notice that it has double bond, single bond, double bond, single bond, right? They alternate like this. Whereas in cyclohexane, the molecular formula is C6H12. So this is a saturated cycloalkane, okay? So we do have the 6 carbons going around here, but we only have single bonds, all right? Aromatic hydrocarbons are so important in organic chemistry, and you might be looking at it and saying, well, that's kind of an intimidating structure, this one here. But they are so important in organic chemistry that we have to cover them right from the get-go. All right, today I spent a lot of time making a video just about functional groups. So what I'm going to do is I'm going to ask everybody who's online right now, all of my students or anybody who's watching this video, to make sure to watch the entire video about functional groups. It's a little long, but again, organic chemistry at the beginning is a lot like learning a language, and you have to be aware of all of the functional groups on this slide for the first exam. Now, if you're like, I have to have this whole slide memorized, not exactly. So let me show you what we consider to be important. The first thing is that this table is kind of funny, the way that they have it written down. The functional group is not really labeled properly, in my opinion. All of these things here, these are the functional groups, okay? Okay, these are the functional groups. So what I have highlighted in yellow are the things that you need to know. So you have to know the functional group: alcohol, aldehyde, amide, amine, carboxylic acid, ester, ether, halide, ketone, alkene, and alkyne. And you have to know their structural formula. Okay, again, I'll just, put a plug in here for my YouTube channel, which is, of course, going to make me a multimillionaire by the end of the semester. So see my YouTube video. I'll tell you what, and if you don't like the sound of my voice, there are probably Avogadro's number of videos that cover functional groups in organic chemistry on the internet. So you don't even have to watch my video. And if you're wondering a couple things here, the first thing you might be like, why do I have to memorize all this from the get-go? Well, the reason why is that functional groups, a seasoned organic chemist can look at a functional group like this here, and she or he could say, okay, well, I know that that's an alcohol. When I have R and then I have an OH, if I see an OH anywhere in a molecule, I know that that's an alcohol. Like, for example, this molecule here is ethanol. That's the alcohol that's found in beer and wine and schnapps, okay? So if if I see ethanol, all organic chemists are going to know the structure of ethanol. But what if you see a molecule that you've never seen before in your life? Well, if it has an OH on it, if it is an alcohol, you'll be able to predict some of the chemical reactivity of that alcohol. So that's why it's important that you understand functional groups. Now, the next thing you might be asking is, what the heck is R? I've been looking at the periodic table and I can't find any element R. Well, it's written down here. It says R, and the R with an asterisk by it represent an alkyl group or an aryl group. Basically, R means, the remainder of the molecule. So it means any part of a molecule that just has carbons and hydrogens attached to it. So what I'm going to do is I'm going to ask you to watch my YouTube video, which covers all of these functional groups in detail. And if we have time at the end of the lecture tonight, I'm going to try to go through as many of these as is possible. All right, so it's 6:03. Is there anybody? Let me see here. Da-da-da. Come on.